So for September camp for statistics, I think this is about where we will be. We will have completed part one, which is about summarizing and displaying data, which is mostly one variable. We'll be entering part two, which is about exploring relationships between two variables, and we'll be sorting through chapters 7 through 10. My guess is that you'll need to be able to do 2 or 3 chapters, 7 through 9. We'll sort of see. So I'm just going to set it all up and know that it'll all be there, whatever you will need. So we'll start with chapter 7. It's about scatter plots, association, and correlation. And many of you are relatively familiar with this, but now we're approaching it from a statistics standpoint, which is kind of neat because we really get to see what's going on behind the black box. So really, anytime we want to look at a set of variables or look at the relationship between two variables, we make a picture. And more specifically, the picture we're talking about is a scatter plot. And you guys are pretty familiar with that. You have a vertical axis and a horizontal axis. And some new terms, sometimes we call this the independent variable and that the dependent variable. In statistics, we call this the explanatory variable and this the response variable. So I want to see how temperature responds to elevation, for example. And then we look for a pattern once we plot our data. And specifically, we want to describe the association. And just like we had shape center spread when we were talking about one variable statistics, when we're looking at the relationship between two variables, our mantra is not shape center spread, but direction, form, and strength. And if we're talking about direction, we want to know, do we have a positive relationship? Do we have a negative relationship? So is it positive or negative? And is it straight or is it curved? And how strong is that? If it is curved, is our data sort of way spread out, or is it pretty clear that one responds strongly to the other? And we tend to say it's a weak, a moderate, or a strong association. So, for example, if we were talking about a drug dose and your pain relief, I think we could all, if we think about what that would look like, the dose would be the explanatory, the relief would be the response, and likely the more you take, the more pain relief you get, but that's going to probably level off. So it's likely positive. The higher the dose, the greater the relief. It's likely curved, and I'm probably strong. It's probably pretty strong. Okay, so if now the association is linear, then we can describe what we call the correlation. In everyday language, correlation is overused and is not as specific. In statistics, we can only talk about correlation if we're talking about a line or data that's straight. And we use R to describe that. That's the correlation coefficient. It's a numerical value that quantifies the direction, because if it's positive, we know we have a positive relationship. If it's negative, we know we have a negative relationship. As cost of something goes up or as price of something goes up, the sales might go down. So it quantifies the direction and the strength. If it's 1, they're perfectly related. If it's -1, they're perfectly related, but negatively. If it's +1, they're perfectly related, but positive. So direction and strength of a linear relationship. How we calculate that is we take a sum of all the z-scores in the x direction and all the z-scores in the y direction, and we divide that by n-1. We might investigate that a little bit more later. You won't necessarily need to compute it. We'll see. There might be a video on that, or maybe we will have done it before you left for camp. So make a picture. Describe direction, form, and strength. We're talking about the association between the two variables. And then if it's linear, we can start talking about correlation. So when we have, if, again, we're going to talk about correlation, the conditions need to be, first of all, do we have quantitative variables? Are we doing weight of a car versus the gas mileage, mileage per gallon? Could we do one there? Sure, those are both quantitative. What about the brand of the car versus the number stolen, or the model of a car? No, we couldn't do that because the model of the car is not quantitative. Then we check to see that it's straight enough, and then we want to look to see if there's any outliers in the data, and if there are, we should if there are outliers, we should find the correlation coefficient with those outliers and without those outliers. And we'll visit more of that later. We'll look more at outliers and influential points. I think that's in chapter 9. And just what about correlation? There are these 7 properties of correlation. They're further explained on page 156. Some of it we've already discussed. The sign will indicate the direction of the association. Again, when elevation increases, temperature actually decreases usually. If temperature goes up, PV equals nRT, pressure goes up, so that'd be a positive relationship. The values of R range between -1 and +1. You very rarely see -1 or +1 unless the data is sort of perfect, like if you were doing a conversion between Celsius and Fahrenheit, something like that. It treats X and Y symmetrically. What does that mean? If I find R for gas mileage versus weight, that's going to be the same as R for weight versus gas mileage. Because if you remember how it's calculated, it's the sum of the z-scores in the x direction times the z-scores in the y direction over n minus 1. So it doesn't matter if you flip those. It's unitless because we're talking about z-scores. It's not affected by changes in scale because we're talking about z-scores. It measures the strength of a linear association. Variables could be, there should be sort of a period there. So variables could be strongly associated, but the R could be low if it's not linear. For example, that the pain relief and the drug dose. It's probably a pretty strong association, but if we graphed that and tried to fit a line to it, our R might be kind of low because it's not linear. And it is sensitive to outliers. An outlier can change that, and again, we'll investigate that later. Also, you have to think about, just because you have a high correlation does not mean that you've got causation. So strong correlation does not mean that one causes the other. We might graph life expectancy to the number of computers in the home and find that there's a pretty strong R value. But does that mean if we give people computers that their life expectancy will increase? No, not likely. There's probably something called a lurking variable there, a hidden variable behind that relationship. Why would life expectancy and the number of computers in home have a high correlation? Well, it's probably more likely to do with your income, and that's called a lurking variable. Something like air conditioner sales and ice cream sales. I mean, does that mean a location that had more air conditioners would have more ice cream sales? No, those are both related to temperature. And then finally, again, this is something we'll investigate a little bit later, but because this idea of quantifying a relationship with an R value is really strong, we might want to straighten a scatter plot. We can re-express data to get it straight, enough to then proceed with a linear regression and determine correlation. And we'll just tap into that. Again, I'll do an example of that on the video, and we'll investigate that much more closely in chapter 10. So I strongly encourage you to read the chapter. If you look over these notes I've just done, watch this video, and then kind of peruse the chapter. That should be a pretty good study of it. And then doing the written exercises will solidify that understanding. And you might need to check the solutions manual if you're not really sure. Well, first of all, you should check your answers, but occasionally you might have to look at the solution and go, oh yeah, I see what they're saying. But you learn that way. All right, give that a go.